Alright folks, EDAD 5062, Spooky Correlation Part 2. Let's take a look at a real life fake data, but real world example of a correlational analysis. Now we have a research question that says, what is the relationship of height, how tall you are, to self-esteem? Okay, and let's take a look. So we'll start out with our data. So we've got 20 people participating in this analysis. We've got heights that range from the high 50s to the 70s. And we've got some measure of self-esteem. It seems to go from the 3s up to the mid 4s, probably some sort of assessment on a 5-point scale. Like we did before with our fictitious IQ examples, we're going to plot our data. So we've got self-esteem running here on the y-axis. We've got height running along the x-axis. They both go from lower to higher. So let's see what these data look like. Alright, so just glancing at the data, take a moment to stop and think, what direction is this relationship? And what do you think the magnitude of the correlational coefficient might be with these data? Now, as I look at it, I think maybe positive relationship. Now, if it were a perfect relationship, it'd probably be this 45-degree angle. So it's not quite that. But, you know, as I look at it, it looks like it's probably a pretty strong relationship. That's what I think. Let's see. There's a line. We could draw a line that goes through that measures, that splits the high values with the lower values. And this is what we'll sometimes call a line of best fit. I'm just guessing here. We haven't plotted this statistically, but I'm just guessing based on the size of and the orientation of the dots there. So let's take a look. Let's walk through an example. Don't be afraid. This is the formula for calculating a correlation. Now, of course, we don't really use these hand calculations anymore. We've got these great little computers that'll do all of this stuff for us as long as we put in the right information. But I'm going to walk you through an example just to see how we used to calculate these things in the old days. Now, our formula is defined down below, where n is the number of pairs of scores. Right? So we had 20, right? Our n is 20. The sum of the products of the paired scores, the height and the self-esteem scores, goes into the equation here. And then we're also taking the sum of the x's and the sum of the y's, multiplying those. We're going to take these two products and subtract them from one another. And we're going to divide all of that by the square root of this bottom equation, where we're taking n, which again is 20, times the square, the sum of the squared x scores, and the sum of the squared y scores over here. Alright, so let's take a look at our data. We've got 20 rows of data. We've got the people with the height that we've seen before. We've seen the self-esteem scores. Now here is the multiplication of, of height and self-esteem. That's x times y here. This is the square of height. This is the square of self-esteem. If we were to add those all up together, we get the sums across the bottom. Okay, so let's walk through this calculation. So again, our x value is height. Our y value is self-esteem. Here's all the calculations that came from the last page. Here's our formula. Let's follow along. Again, this is our n, 20, times our sum of our products of x, y, minus the sum of x times the sum of y, divided by this crazy set of numbers down here at the bottom. Let's see our next step. Alright, so we've come up with these two products. We're going to subtract them from each other. We're beginning to calculate some of the values underneath the square root. We end up with 521.2 divided by the square root of 7376 times 6899, which ultimately solves to 521.2 divided by 713, which gives us a correlation coefficient of 0.73, positive and relatively strong, greater than 0.65, which is our strong benchmark. So let's take a look at the plot. Okay, so one of the things that we are oftentimes concerned about with correlations is there actually a relationship between them? We see things, we might see relationships that don't make sense. Alright, so let's take a look at those, and let's think about what we might be seeing here. It turns out that the correlation between alcohol sales and the number of churches in a community is high. We see a high correlation between these two things. Do we think there is a meaningful relationship between the number of churches and alcohol sales? I don't know. We find also that there is a positive association between the number of firefighters at a fire and the amount of damage of the fire. So do we think that we should send fewer firefighters to a fire and there'll be less damage? I don't know. We can talk about that. Finally, we find a positive relationship between a child's shoe size and their achievement on a math test. I wonder what that's all about. All of these statements and findings have the same problem. What's that problem? Correlation is not causation. In each of these cases, an unmeasured third variable is at play in the reason why we find these two things together. First, what about our alcohol sales and churches? Again, I wouldn't think that the number of churches causes alcohol sales, or people get super drunk and want to go to church because they feel guilty. Instead, we find that in areas of high population, there's lots of alcohol sold, and there's lots of churches. The more people, the more churches, the more people, the more alcohol. What about our firefighters? Well, it turns out when there's a really big fire, there's lots of damage, and we also send lots of firefighters. So in this case, size of the fire is the third variable that's resulting in both of these things. And then finally, our shoe size. It turns out that children with larger feet tend to be taller and older. And students who had more math instruction tend to do better on math tests than the student with smaller feet, less instruction, fewer years in school, taking the same math test. So it has nothing to do with shoe size. Right here, what we're talking about is age. Alright, We'll pause for part 3.